Okay, so good day to each and every one of you. This will be part 2 for this problem. A cantilever beam with a uniformly varying load equivalent to 360 pound per foot, and the length of our member is 12 feet, having this external load here at point A equivalent to 1000 pounds. So our goal for this lecture is to determine what would be the value of this V, shear load, and this value M, the bending moment here at this section. So if we're going to use the approximation again, since the whole length of the beam is continuous from 0 to 12, means to say that our limits, okay, in order for us to approximate, x should be greater than 0 but less than 12 feet. Okay, so if we're going to replace x here by 0, so let's say replace this v sub 1, so 0 multiplied here, so that will be 0, so v is equals to 1000 pounds. And if we're going to replace it by 12, the answer for that one should be negative 1160 pounds. Okay, and let's replace m by 0. That should be 15 over 3. That's simply 5x. Okay, 5x cube. So replacing x by 12, that should be, this one is 0 of course because we both have x's here, so 0, any number multiplied by 0 is 0, pound foot. Then m sub 2 is equals to, replacing this by 12, that should be 12,000, and then 5 multiplied by 12 cube, that should be, the answer is positive 3,360 pound foot. Okay, so now we have the values for v sub 1 replacing it by 0, v sub 2 replacing it by 12, m sub 1 replacing it by 0, and m sub 2 replacing it by 12, because the whole beam is continuous, its length. It doesn't have any other sections, and it doesn't have any other segments. Now we managed to solve for this 4. The next step is to graph. At this portion at A, it has a 1000 pound force going upward. So we are going upward. This one is 1000 pounds. And the next one, since we have this 1000 pounds and then we also have 1000 pounds upon replacing x by 0, so means our answer is correct. So if we rise up 1000 pounds and replacing it by 12, means to say that a distance less than 12 feet, the shear force is equivalent to negative 1160 pounds. Okay, if you can remember that we have here a reaction R sub B equivalent to 1160 pounds, right, going upward. Since this V sub 2, our initial assumption was going down. If we change the value of this negative 1160, negative sign, to positive, it should be going upward, right? In order for it to be positive. So we have here RB 1160 pounds, so positive, you're going to change the sign. So also net positive 1160 pounds, so it's the equal. So since our initial assumption was going down, it should be also going down. Goes like that. Okay, it's a curve because the degree of power of this equation is squared, means to say that it should be parabolic again. Okay, since we managed to go down negative 1160 pounds, negative, so we have this positive 1160 going up, so we will go back down to 0. Okay, so this is the shear diagram and this portion that is inside our graph. Okay, now upon doing that, the next step is for us to determine the bending diagram. This time is for the bending diagram, and for us to do that, since we have here a portion of the beam having that concentrated load, if you can remember, that was 2160 2160 something, should have another line going downward. Okay, that represents the concentrated load of this 360 pound per foot. And at that portion of the graph here in the shear diagram, there is a point where V is equals to 0. As you can see here in the graph, where it intersects with the horizontal axis and the axis going downward along the vertical axis by the concentrated load 360 pound per foot along the whole span of this member. Okay, so that's why we have this downward axis in our diagram. And upon the intersection point of the shear diagram and this point, that is the value where V is equals to 0. And according to our previous lessons, that if V is equals to 0, that is the point where we can find for the maximum bending moment, right? So let's try to find first the distance of this portion. And in order for us to do that, we need to consider again using the formula for the shear load formula for our beam. So that should be V is equals to negative 15 x squared plus 1000. Since V is equals to 0, for us to solve for the distance of the maximum bending moment, this should be 0 is equals to negative 15x squared plus 1000. Solving for x, that should be x squared is equals to 1000 divided by 15, and then square root both sides. Okay, use the simply square root both sides. The answer for that one should be approximately 8.165 feet. Okay, so this one refers to the distance here, because this is the starting point all the way to this portion. So this one should be 8.165 feet. Okay, since we managed to solve for x, the next one is to calculate the maximum bending moment. How are we going to do that? Let's go back here on the formula for our bending formula. So M sub max is equals to 1000 multiplied by this one, 8.165, minus that's simply 5 multiplied by 8.165 cube. So the maximum bending moment should be equivalent to approximately 5,443 pound foot. Okay, so let's try to graph this one. Our first value for the moment, if we replace it by 0, is 0. So we're going to start here and replacing it by 12, that was positive 3,360. Okay, but before that, we need to graph first this 5,443 pounds. So let's move a bit downward. Let's go here. If this is 0, this is the graph for the bending moment diagram. And don't forget that the degree of power of the bending formula here is 3, means to say that still parabolic. So it should be going to 5,443 pound foot. And where can we find that? Where the shear load or shear force is equals to 0. So we're going to climb up at 5,443. Okay, this portion, that is 5,443 pound foot. And let's go down to 3,360 pound foot. Okay, and then go back to 0, because that is the end of the beam. Don't forget that we have here M sub B equals to 3,360 also. So all we need to do is to go down. So this portion is 3,360 pound foot, and then return to 0, because that's the end of the beam. So this is the bending diagram for this sample problem. So this one is 0. And basically that's it. And we managed to finally solve the shear and bending moment diagrams for this problem. I hope you learned something out of this, and check out my other videos for mechanics of deformable bodies.